Now, can you tell them, because they are not going to repeat, I mean, just who you are, with whom you work?
Yes, okay.
Just introduce yourself.
Mm-hmm. Okay. Yeah, my name is Rafał Świętek. I'm a fourth year graduate student at Institute of Stefan with Lev Vidmar. And I'm graduating this year. And Leah invited me to give a talk here and to spend 3 days at Connecticut, which so far very nice. I really enjoying it. Connecticut is beautiful, although small. Yeah, it's very good.
Very nice,
for sure. But also the atmosphere is really nice. Okay, essentially what I will be talking about today is a collection of my research during my PhD, which concerns the topic of how you're going from a perfectly ergodic system towards an ergodicity breaking transition to localization, integrability, etc. And I will mostly focus my work on these three papers. The fallouts I should have removed. And in my talk, first of all, I also want to mention my collaborators, whom some of you might know. Miroslav was a postdoc in Ljubljana and he moved now on to Wrocław. Max is a colleague, PhD colleague of mine. Patrycja, Marcin are researchers at Wrocław. Karla, Antonella, and Trieste. And Marcus and Leo, I think all of you know very well. So in my in my presentation, I want to discuss firstly a general introduction to what I mean by thermalization, what is the concept of ergodicity, quantum chaos, etc. Then I want to move on to the first topic where I show you how ETH, which is a sufficient condition for thermalization in isolated many-body systems, is broken as you approach the critical point. Then I want to move on, what is the connection of the phenomenon which we dub there as fading ergodicity, which is the breakdown of conventional ETH, how it connects to maximal chaos. And if I have enough time, in the last few minutes, I want to discuss a scaling theory based on entanglement, which determines the essential properties of system undergoing fading ergodicity. So firstly, let me discuss a general introduction and introduce some nomenclature which I'll be using in the talk. So whenever I'm thinking about non-equilibrium physics, I usually put three main pillars, which are for me the main important question when I think about systems out of equilibrium. First and maybe one of the most important one is transport. Whether once you have a localized wave packet and you're interested in how this wave packet spreads in time, you can essentially classify this four main distinctive transport properties. You can have ballistic, which is a linear light constructor. You can have diffusive, which is mostly found in chaotic system and which is also known from Brownian motion. Then you can have something which is called subdiffusive, which is much slower than diffusive transport. And a very special kind of transport, which is superdiffusion, found whenever you have SU2 algebra present in many-body systems, but I will not discuss this in more detail. Secondly, another important question is, when you have initialized an initial state in your quantum system, and you know that at a given site, you have your particle is, let's say your spin is parallaxed upwards, or you have a particle given on some site, and then you want to evolve your system in unitary dynamics. What actually happens is that while initially your system was overall pure and also locally pure, this local purity decays in time and you become locally thermal. And essentially after long enough times, your distribution over particles, for instance, is uniform and you're thermalized. So what's the key property here is that an initial bit of information is completely lost under unitary quantum dynamics for chaotic systems. And the last question, whether overall a system taken out of equilibrium will reach a stationary state, which can be characterized by a thermal ensemble. And usually what we mean by that is whenever we look at an expectation value of our observable, we want to compare the long-time dynamics to a thermal ensemble, which here I pick the microcanonical ensemble. And there was a very nice experiment in the Trotsky group where they initialized the system in a charge density wave, which is highly non-equilibrium. They let it evolve and they saw that the density profile spread uniformly through the entire lattice, indicating thermalization. But what is a common property of this kind of system? What is the driving force leading to all of these different phenomena. The current understanding is that quantum chaos is a common property of all these various kind of systems. And what do I mean by quantum chaos? Classically, chaos can be defined by exponentially divergent trajectories, non-zero level exponents, etc. And the quantum for quantum system, that's much less clear. But in the 80s, there was the seminal work by Bohijas, Janane, and Schmidt, showing that if the spectra of a quantum Hamiltonian matches that of a random matrix, then the semi-classical limit of your system has chaotic dynamics. And this kind of analog we also use in many-body systems. Whenever our spectral statistics or the levels of the eigenstates matches that of a random matrix ensemble, we say that the system is ergodic, is quantum chaotic. And how do we actually probe this quantum chaos in many-body systems? What you can usually look at is your energy spectrum, how your level spacings, distributions of your level spacing behave, or how your levels repulse each other, known as level repulsion, which is indicated by, here in this plot, by the zero vanishing probability at zero level spacings. This is known as level repulsion. Whereas whenever you break quantum chaos, whether you're non-ergodic, you have a Poissonian distribution, which is exponential power law in the level spacings. Secondly, you can look at eigenstate properties. Here I show you for the eigenstate entanglement entropy. Whenever you prepare your system in an initially pure state, an eigenstate of the Hamiltonian, you trace out some part of the system, for instance, half of the entire system, and you can study the Feynman entanglement entropy of this reduced density matrix. If your system is quantum chaotic, your eigenstates are effectively behaving as high random states, and the prediction for high random states is that you have a volume law entanglement where the coefficient is maximal. So here I show you exactly that the entanglement is proportional to the volume of the subsystem times log 2. This is known as maximal entanglement, which will become much more important when I will discuss integrability. And this was also shown, if you're interested more in the topic, there's a recent review about entanglement, where they show how entanglement behaves for chaotic systems with or without conservation laws, Gaussian systems, free fermionic systems with translation invariants, etc., etc. And last but not least, maybe the most important aspect for my talk is the eigenstate formalization hypothesis, which presents an ansatz for your matrix element of your observable, where your diagonals have a smooth dependence on the mean energy, where on top of that you have exponentially suppressed fluctuations, and the exponential suppression is given by the density of states, or your thermal entropy, if you wish. And the off-diagonals are solely suppressed exponentially by this density of states term. And if this condition is satisfied for your matrix elements, you can show that your system will thermalize for any initial state for this given observable. Maybe not any, but for the majority, to be more general. And this was originally introduced by Deutsch and Schrednicki, and later by Marcus Rigolo, was brought to lattice systems. And since I told you that my talk will mostly characterize what happens when you go away from quantum chaos, when you go towards a ergodicity breaking transition, I want to first discuss what are different possibilities of ergodicity to be broken in quantum systems. For now, I want to first flash you two main pillars, directions, let's say. One is integrable systems, which are usually a singular point in a parameter space. That means that if you have the overwhelming majority of your systems is thermal, is ergodic. But if you tune your coupling such a fine-tuned way, you can find some integrable points in your parameter space. Paradigmatic examples are like the quantum Newton cradle, which was here shown with the group of David Weiss, and the XXZ, XYZ model, etc. And a different point of view can be seen for the disorder systems, the supposed many-body localized systems, where very large on-site disorder causes the system to localize in your lattice, and essentially violating quantum chaos in general. And both of these systems were observed experimentally on short time scales only. That's why the whole question whether MBL is a new phase of matter or not is still open, because we cannot resolve it so far. with a small difference that for the integrable case, even though David Weiss studied short timescales, he still showed that after the system equilibrated, he still didn't see thermal thermal ensemble predictions, which means that the timescales he considered were actually sufficient to show integrability in this model. Both of these directions don't thermalize, they lack thermalization, while the integrable interacting equilibrate but not thermalize. And here the important question is, does it imply that there is violation of quantum chaos for these kind of systems? And of course, these are not the only examples where you can see where you go away from ergodicity. Now going back again to the interacting integrable, you can also see that on the level of entanglement, where we, in a recent study last week, showed that interacting integrable models, while they have also volume law, similarly to the quantum chaotic systems, but the volume law coefficient in front is much smaller than 1, which means that the volume law coefficient can be seen as a indicator whether you have chaos or not. Then you can look again at the many-body systems, many-body localized systems. Yes, of course.
What is the difference on the system side?
For interacting integrable,
SG that you said?
this is system size independent. It's just dependent on the subsystem fraction. So F is the fraction, is LA, so the subsystem size divided by the entire system. So this simply means that interacting integrable have also volume law, but there's just some number in front, which is, yeah, it's smaller than 1. Yes, exactly. Yeah, exactly. But there's also the distinction that for quantum chaotic, there's no subsystem size or subsystem fraction dependent term. But here for the Gaussian or interacting integrable, there indeed is this kind of dependence, which is usually non-trivial. And now on the level of mathematical localization, yes, of course.
Yeah, okay, so we only look at interacting, no? Okay.
Yes.
The blue and the orange. Okay.
Yeah. Because the prediction for non-interacting, you can see like for the Gaussian, these are essentially non-interacting systems. And the red one, yeah. And for this system, there's an analytical prediction how it behaves. And also translation invariant preferment, there is some prediction which is not exact, but there's some good approximations.
It's a little above the non-interacting.
Yes. And the system size dependent, which I don't show here, it looks like this goes down towards either of these two predictions. So interacting integrable systems are much closer to non-interacting than to quantum chaotic. And then next, the many-body localized systems, how you can detect, for instance, the transition is when you look in terms how ETH is violated. You study the eigenstate to eigenstate fluctuations of some observable. Given by ETH, this quantity decays as with the square root of the density of states. But if you localize, this should not decay at all because you have outliers which essentially become order 1 in your system. And here what was seen is that indeed there's a slowdown of the decay of the eigenstate to eigenstate fluctuations, but yet again it's not easy to show whether there's a fixed transition or not because this still looks like it slowly drifts for larger values. Then one can look at many-body scars, which differ in the fact that you have a bulk of the spectrum which behaves perfectly thermal, like quantum chaotic systems, but you have polynomial number of outliers, which have areal entanglement or logarithmic entanglement, which behave as non-thermal state. And these kind of states cause very special initial states not to thermalize, and they can even show perfect revivals in the dynamics, and you can have coherent oscillations for infinite times. Then you can also consider kinetic constraints models where you have not polynomially but exponentially many outliers, and your fluctuations decay polynomially with system size x instead of exponentially as for the ETH. And last but not least, quadratic or non-interacting systems. While they violate ETH itself, they have something which is called weak ETH, because the variances of your matrix elements, of the diagonal matrix elements, decay polynomially with your system size. And here, an interesting fact is that quadratic systems which have single particle chaos have this property, but if you look at, for instance, Aubry-Andre models or Anderson insulator for very large disorders, you will see that there's no wiki-th because all diagonal matrix elements will be system size independent and become order one. They will not decay. But I will not talk about this in more detail, but feel free to ask me if you're interested. And what are prototypical models to actually study the breakdown of ergodicity in quantum systems? The first model is what I already now said, is the Anderson model, which consists simply of a single electron hopping on a lattice, where the lattice has random on-site potentials. If the on-site potentials are very small, then the particle can spread the entire lattice, it can hop anywhere, and your wave functions are delocalized, which is this picture on the left. But if your disorder becomes too large, then because of interference effects of your particles with the disordered landscapes, the wave functions become exponentially localized around some localization center. And there's a fixed disorder strength, which separates these two phases, and which indicates an ergodicity breaking transition for this single particle Hamiltonian. And in terms of level statistics, it is also shown very nicely that at this critical disorder strength, your level statistics come from a Wigner-Dyson distribution, which is known for quantum chaos, to a Poisson distribution, which is known for non-ergodic systems.
Did you say the dimension?
This is 3D, yes.
Oh.
Yes, sorry, this is 3D. I will, later in my talk, I will mention in more details about smaller dimensions, but the transition happens only in 3D and above. Yes, that's a good comment. And one very interesting to me remark is that while this model is a very, very nice paradigmatic model for delocalization transition, it's also a model for diffusion itself, which was not trivial at the time where this model was initially proposed. And secondly, the model which I mostly study, the quantum sun model. Here I'll go a bit slower because this model is rather complex. So the quantum sun model consists of a thermal grain where you have order one number of spins, which we pick, for instance, to be 3, and we fix this number. And then you have L spins outside, which are localized. The interaction is only between some randomly selected spin in the grain to the spin outside of the grain. So the coordination number of this system is 1. So you can effectively say that it's a zero-dimensional model, even though there's some form of distance because the interaction is decaying with this distance. And how we write the Hamiltonian, we simply write it as the thermal grain, which we model by a random matrix. We have the on-site disorder outside of the grain, which localizes the particles. And then we have the interaction, which are simple hopping processes.
But it's more than hopping, right?
Yeah, it's like spin flip. It's also, yeah, you can create, yeah, exactly, yes. It's like spin flips, but yeah, yes, exactly. It's U1 non-conserving.
It's just to indicate some are up and some are down, and there is nothing special about the red and the blue there.
No, there's nothing special. In fact, you can actually tune this disorder to be always positive, but still random. Then all spins should be probably up. That's a GOE matrix. That's just to model this random grain in the middle. So the GOE matrix of dimensions 2 to the n by 2 to the n, so it's very small. And then we have this couplings to this GOE grain.
So, let me try to understand. So in addition to the spin part, you have a random matrix embedded there.
Yes. So here we embed the random matrix by hand. And this model was introduced to study the avalanche effects and disordered spin chains, that you have these resonant regions which can expand in space. So in this model, we put this resonant region or this thermal inclusion by hand to show the avalanche in action, so to say. So we induce it by ourselves. And the exponential coupling is modeled such that if the coupling is large enough, then the avalanche will expand, so the entire system will delocalize. But if the coupling is too small, then the avalanche will at some point stop and the system will not be able to delocalize entirely. So some spins will remain localized if the interaction is too small. And in fact, one can show both analytically and numerically that there's indeed a transition. And as I said, by the criterion that the interaction has to be strong enough. What I mean by that is that the interaction to the last spin, which is weakest coupled, which is roughly alpha to the distance L, should be larger than the mean level spacing or square root of the mean level spacing. And if this is true, then you in fact will find ergodicity. And this was also seen numerically again for the gap ratio and for a lot of other different quantities, which I will not show now.
So the transition happens in one point, one value of
Yes.
alpha. Why did you put that gray?
The gray line is put there because there was let's say error margin between two different quantities showing the transition, because there are finite size effects which can be different for different quantities. Analytically, the transition should be here at 1 over square root of 2. But of course, yeah. I mean, if you think about it, it's not so far compared to other models. Yeah, the scale is very small, so it's not so far. In fact, now this was published like 3 years ago, but now we improved and we can actually put it a bit closer. We know how to minimize the finite size effects, but they are still present, and we have to live with them, sadly. And now let me go to the first topic where
you would have minimal finite size effects if the ratio n over L, if you are able to minimize it. N being the thermal grain and
yeah, I mean the n should always be smaller than, I mean n should not scale with L.
right.
So n should be larger, but should also not be too large for your finite systems.
Okay.
So we pick usually n3, but you can pick n5.
Right.
Which is already large, but not too large, because you still have, let's say, 11 spins outside. And in this case, you are much closer to 1 over square root of 2.
Okay.
So the larger the grain or the larger, you can also change the prefactor gamma or prefactor G naught. And if you increase those, so you effectively increase the strength of your grain, then you will be also closer to the 1 over square root of 2 prediction.
Okay.
There are a few parameters you can essentially tune, and you can minimize the finite size effects by that. And now let me discuss how in these kind of systems, specifically the quantum sun, so many body systems, how it actually happens that you have perfect ETH in some side, then you have localization on the other side, and how actually these two connect. So the question we wanted to address is how ETH is broken in many body systems. And there you can consider two scenarios, that you have perfect ETH on one side, and then a sudden discontinuity, and you have perfect non-ergodic behavior on the other. Or you can have an ETH phase, some smooth slowdown of dynamics until you go to the critical point, and then you have a non-ergodic phase. What I will argue is actually that the scenario B here is the one which is relevant for isolating many-body systems. Let us now look again at the ETH and consider how actually ETH can be broken. There are already several studies showing that ETH itself is not sufficient enough to describe all dynamics of the systems, because if you look at higher order correlation functions like out-of-time order correlator, then you know that ETH predicts the wrong kind of dynamics, which is found experimentally or numerically. And there are several studies which try to address these higher order correlation functions, but I will mostly focus on 1 and 2 body correlation functions where this problem is not present. And how do we address the breakdown of ETH? What we actually consider is that the suppression term of the density of states at smaller frequencies, we simply state that this suppression term becomes weaker and weaker. And in fact, what we do at small frequencies, we say that the suppression term is substituted by some factor eta in the exponent, which diverges at the critical point, which means in the ETH phase, eta is equal to 2, but and as the transition diverges, so there's no decay of your fluctuations in your matrix elements. And everything in between, we denote as fading ergodicity, which is not consistent with conventional ETH, but it's still consistent with thermalization. So your model still thermalizes, but at much longer timescales. And in fact, the timescales here in fading ergodicity become exponential with the number of degrees of freedom of the system. So even much slower than subdiffusion which you would find for local Hamiltonians. So that's a very strong and consistent slowdown of your dynamics until your dynamics become so slow that even the smallest energy spacings do not resolve these kind of dynamics anymore. So you go below the Heisenberg timescales. And here to show you some numerical results, how it actually happens, how it actually happens to your off-diagonal matrix elements if fading is present. Given that you want to satisfy the sum rule, that the sum or square sum of all of the diagonal matrix element is still D, and you want to say that at small frequencies the suppression is weaker, then you have to compensate at large frequencies with a much stronger suppression. So you have this compensation where we have at lower frequencies an increase and at small frequencies a decrease of your suppression of your diagonal matrix elements. Here what I actually plot is the coarse-grained average of a local magnetization as a function of frequency, and we scale it by the density of states. If ETH would be satisfied, then all of these curves would collapse, indicating consistency with ETH. But since ETH is not fully satisfied, and we see here an increase and here a decrease, we need to come up with a new framework. And this framework is finding ergodicity, where I want to argue that there is this intrinsic energy scale, the relaxation rate of Taoist energy, which is separating the RMT dynamics from local Hamiltonian dynamics. And this energy scale is exponential within the degrees of freedom, which causes this increase at small frequencies of diagonal matrix elements.
Just for me, this is slowly. So that value of alpha that is selected is the value of alpha where you're already outside the
ETH, exactly, yeah.
And then you cannot collapse. But if it was in the ETH,
it perfectly collapses. Yes. For the quantum sound, it's actually just a singular point. Only alpha equals to 1 is perfectly ETH. Whenever you go alpha below 1, or maybe 0.99 is also ETH, but it's hard to say.
And it will get worse and worse as you...
Yes, it gets worse or worse as you go to the transition.
And then, okay, but then from that rescaling, you're going to extract that gamma.
I mean, the gamma we first rescale from the fits because we fit a Lorentzian to this kind of structure. And from that, we have the gamma, which is the width, and then we can still collapse the curves. Yeah. And this collapse of the curves indicates an important property, which I don't write out here, is that the off-diagonal matrix element at slow frequency, how they actually depend, they depend on your mean level spacing divided by gamma, by the width. So with the width would be polynomial or even order 1, typically found in local Hamiltonians. And then the mean level spacing is the leading factor, and you see consistency with ETH. But since your gamma is exponentially small, this causes this increase, this slowdown of dynamics, and the increase at small frequencies of diagonal matrix elements.
And we are looking at SZ, no?
Yes.
Because I think you're going to tell us about SX, right, or no?
I have some backup slide about SX, so I can show you later. But I will mostly focus about the Z, because this is a relevant observable which indeed sees the transition very well, and also has the smallest finite size effects. So there's also an important question, which observables see fading ergodicity, because there are some observables which, as you mentioned, SX, so like a correlator in SX. This quantity does not see transition, but it also satisfies ETH on the localized side.
Yeah.
So it's simply not a good indicator. But SZ is a very good observable because it's very close to a conserved quantity of the localized side. That's why it sees so well the transition point. Now, what are consequences of the fading ergodicity? As I already motivated, you have the slowdown of dynamics. And to quantify that, you can look at, again, this eigenstate to eigenstate fluctuations, or the scaling of the diagonal matrix element at a given omega, which is in the plateau. And both of them, they decay exponentially with system size, and the prefactor and the exponent becomes slower, weaker and weaker, such that it will simply be non-decaying at the transition and at the localized site.
You have to 23. The
Yeah.
value.
I mean, yeah, that's a fit,
But
so
I would expect so big fluctuations there that it would be hard to do that.
yeah, but eta is like in the denominator.
Yeah,
Yeah, you're right. I mean, it's hard to say. Here, the closer we go to the transition, then of course we have the extraction of eta becomes even more complicated.
Mhm.
I mean, if you look at the y range, these are like 2 orders of magnitude, so
yeah.
it's very difficult to say anything very consistently. But the scaling seems very, I mean, argue very precisely what eta should be, but the scaling just seems consistent with the theory that we want to present.
Yeah, and the system size goes up to 13.
Yeah.
Because the dimension is 2 to 13, right?
2 to the 16, because we have
Yeah, right. for sure.
we have the grain n, which is 3, and to the 16. Yeah. And to fully now prove that thermalization is still valid, we need to also look at the what is called the outliers of the eigenstate eigenvalue fluctuations. And these outliers, as a matter of fact, decay in the same way as the average, which indicates that you again have that they in a sense prove that you will still thermalize at a given time scale, which is smaller than Heisenberg time. And if you now extract from all of these quantities the eta exponent from the fits, and this I plot to you in panel D, and we can compare it to some analytical prediction we have for the exponent eta, and they agree remarkably well with the analytical expectation. But even if they wouldn't agree, they still diverge at the critical point, which is the essential point which we are trying to make here. And now to look at a more dynamical perspective, we also prepared the quantum current experiments where we consider the expectation value of the SZ and the correlation function SZ in some initial state. This initial state we choose such that it's in the middle of the spectrum and it's narrow in energy, so we don't take the edges of the spectrum into account here. And to show thermalization, the diagonal ensemble, so the long-time dynamics of this prediction, should match the macrocanonical ensemble. So,
now that I got curious about the edge. So you pick an initial state, it's not a product state then.
it is a product state. It's a product state.
But what did you say that you don't, the product state, once I project in the energy eigenbasis, we have tails.
There are tails, but they are very small at the
They're
edges.
very small, but do you do anything with them? No.
No,
you
no.
keep them.
We keep them, yeah. But we want to say that they are small, so the edges will not
Don't
contribute so much, yeah. There are like subleading corrections to that. Because it's very hard to prepare really a state which is only very narrow energy to have it's never really narrow in energy.
That's why I thought, are you cutting them?
No, we are not projecting. We are keeping all, but they are very small, so they don't contribute very much. And in fact, if we now look at the difference between the diagonal ensemble and the macrocanonical ensemble, we can again scale it with L, and indeed it goes to 0, indicating thermalization. And in the bottom plot, just to show again that since we had the Lorentzian wave function, it's very consistent with the fact that our autocorrelation function has an exponential decay, and the exponential decay matches very well to the plateau of the spectral function. So everything here is very consistent. And at long times, we indeed approach the diagonal ensemble at finite times, which is also relevant for these time dynamics.
The dotted line, which is the saturation, did you mark it numerically or you got it analytically? Oh, no, analytically, no, meaning with the components of your initial state.
Yeah, it's numerically. It's numerical with the component of the initial state. So the dotted line is really simply this QDE, which I show on the here.
Right.
So it's really this evaluated this.
But you marked that you didn't compute from the dynamics at very long times. You use this.
Yeah, we use this. Yeah.
And this is the this is for the C. This is the no.
This for the Q, but for the C you calculate analogously. Yeah. For the Q we calculate the other one, which is there's
there are more.
Yeah, here's an additional term which is SZ. Yeah, it's SZL squared. There's a little bit different for the C, but it's straightforward to find it. And so this is very consistent. And now I want to go to the first consequence of ergodicity, how it actually connects to the emergence of maximal chaos at the transition. And here it's now very relevant to distinguish maximal chaos and maximal ergodicity, which is now a very open topic in the literature. Because what we think of chaos, we always think maximal chaos or that's maximal ergodicity, we are maximally thermal. But actually what I would say is that if you're closest to RMT, you're actually maximally ergodic. Because chaos itself is a sensitivity to perturbations. So if you're in the thermal phase, you have low repulsion and you're very sensitive to perturbations. But once you approach the transition, your energy levels start to cross with each other. Then the sensitivity to a perturbation is even much larger, given by the fact that you have this kind of non-trivial level dynamics. So if the sensitivity is, if you approach the transition, the sensitivity will increase. So you're even more chaotic in a sense. So this will be a distinction between maximal chaos and maximal ergodicity. And
No, this is nice. You said we can just digest. This is Anatoly's.
yeah, that's
way
Anatoly's,
of-
yeah, exactly, yeah.
Greek.
Yes.
But okay, can you repeat slowly? So then you're saying, approach to random matrix is ergodicity. I agree.
Yes.
And then you said the most chaotic case is close to critical point,
Yes, exactly. Yeah.
which is Anatoly's view.
Yes.
Once you have a little perturbation, then the thing changes.
Yes, exactly. Which is the connection to like the classical actual chaos where you have the exponentially divergent trajectories, let's say. In quantum case, it's difficult to actually quantify it. But there are some indicators which I will introduce in a second. And they indeed show that there's a maximal sensitivity at the transition to non-ergodicity.
And just now, ergodicity is close to random matrix, but nothing will be equal to random matrix. Now we just approach.
Yeah, of
Yeah.
course. If you have a low grammaton, you will never exactly random matrix.
But so we should not call it ergodicity, we should call it quasi-ergodicity or something. Ergodicity for me is random matrix.
Yeah, that's true. Yeah, I don't know how to call it maximal mixing. Yeah, it's hard to say. I will call it ergodicity because it's close to random matrix, but it's never exact. I agree. And the indicator which actually can show this maximal chaos is originally introduced to the study of ground state phase transition, is the fidelity susceptibility, where you essentially study the matrix element of your perturbation divided by the level spacings. If you study this for the ground state, or if n is 0, then what people found is indeed some peak at the critical point for various systems where you have a ground state phase transition. And in the past few years, there's a generalization of this quantity to excited eigenstates, where you simply take here instead of the ground state some excited eigenstate. And if you consider either the typical of these states, of these fidelities, or the average, you will see that there is indeed also a peak, but this peak coincides with the ergodicity of breaking phase transition. And for the system that was usually studied, this system have an ergodicity breaking phase transition which goes towards the integrable point, because these systems study integrability breaking. So you have a fine-tuned point which is zero coupling, which is integrable, and everything away from that is non-integrable. But for finite system, you have some crossover region. And for these systems, AGP was shown to be a very good indicator where we actually break ergodicity, so which is given by the peak. And this peak scales towards 0. And what we wanted to see is how this phenomenology applies to the quantum sound model, where we have the tools which are spreading ergodicity, and we know exactly where the transition point should be.
So this plot that you were showing there with the function of delta is some of these these.
Yes, exactly.
Okay.
It's the Heisenberg model, XXZ model with next nearest neighbor couplings.
And so they are showing that tiny delta, you had that change, right?
Yes.
Mhm.
And the thermodynamic limit, any non-zero delta should give you non-ergodicity, non-integrability. Yeah, they consider the typical. There are some caveats which one is better to compute, which I will not go into very much detail about it, but we can discuss later. Because if you consider the average, you have to take into account that this quantity is dominated by very small level spacing. So you want to filter out the very small level spacing, which are usually non-physical, or they are simply finite side effects, because you can have accidental degeneracies.
He knows, but he didn't know my quantity. Yeah, remember that? Okay. Now, this quantity, the susceptibility, I think you can connect with quantum feature information.
Yeah, it is, yes.
If you-
Yes, there are actually connections, exactly, yes. Yeah. Actually, you can show exactly the connection to quantum Fisher information. I think it's simply like a derivative of quantum Fisher to the perturbation or something like that.
Yeah.
I don't remember now. Mm. And now we want to show the same phenomenology for the quantum sun model.
Mhm.
And for the quantum sun model, what we actually know, given that we know that we have fading ergodicity, we know how the matrix elements should scale once you go to the transition. I will not show the entire derivation, but you can show that this term is dominated by the level spacings close to the mean level spacing. So at very, very small level spacing in the plateau of the spectral function. And in the plateau of the spectral function, we know how the diagonal matrix elements scale. So using these two ingredients, we can show that the average or typical fidelity susceptibility have actually this kind of scaling where fading ergodicity enters here by the exponent eta. And up to polynomial corrections, this scaling shows you that D is your Hilbert dimension. Then the typical fidelity scales with D to 2 minus 2 over eta. And this scaling is consistent with first ETH, where eta is 2 and fidelity susceptibility scales with D, which is consistent with previous studies. And at the transition, where eta becomes infinite, is consistent with maximal chaos, which was shown also for the integrability breaking case. And now to show that this also works numerically. But first of all, if you consider the average fidelity susceptibility, we introduce something which is called the regularization. And this regularization enters here the denominator as mu squared, roughly, absolutely with some corrections. And if you introduce the regularization, you actually can show that in the ETH, the fidelity susceptibility depends on this regularization parameter mu. You can think of it as a cutoff in a time dynamics where you probe your time dynamics till times which are 1 over mu. But I will not show details, but feel free to ask me if you're interested. And now looking at the typical and the average, what we see is that indeed they both develop a peak, which is very close to the critical point, and even scales towards the critical point, which we show here in the inset, where we show the scaling of the maxima, then indeed go toward the critical point. So this is very consistent. On the localized side, we don't have any predictions, but here we start to notice differences between average and typical, which we try to now understand more in detail. And now using this analytical expression for the scaling and the fading regime, what we can find is that if we scale our fidelities by this psi fading, we see perfect collapse both for the average and for the typical fidelity susceptibility. Surprisingly, we find also collapse for the average fidelity susceptibility on the localized side, which is very intriguing and still an open question why this actually happens. Because here we don't have really an expectation what eta should be on the localized side, whether it's some form of a localization length or not, and it's highly non-trivial. But it seems like a very interesting coincidence that it works so well. And to fully show that indeed we have maximal chaos, we have to look at how the peak of this fidelity susceptibility scale with system size. And indeed, if you look at how the pairing scaling, the maximum scales with system size, it should scale as d squared or as the square of the density of states, which we here plot in this figure, and we see perfect consistency with the maximal chaos. And here we wanted to go one step further because we know that this model has what is known as a mobility edge, and we wanted to probe how you can use fidelity susceptibilities to actually track the mobility edge. And what is the mobility edge? It's simply an energy-dependent critical line in your energy interaction or disorder landscape. So we can think of ergodicity breaking transitions both as interaction or disorder-driven or as energy-driven at a fixed parameter in your system. And you have various models which have mobility edges or which are in favor of mobility edges. But there are also systems which are against mobility edges, and even theoretical studies saying that there should not be any mobility edges for many-body systems. And these two examples I showed you in this talk, the quantum sun model and the Anderson model, they both indeed have a mobility edge, which was proven both analytically and numerically in various contexts. I will now still focus mostly on the quantum Sun model. In order to study the mobility edge, we need to generalize a fidelity susceptibility to some microcanonical window, where the where the energy density we define simply by rescaling it to 0 and 1. So we subtract the ground state and divide it by the bandwidth. So our energy densities are normalized to 0 and 1. And at a given energy density, we calculate this quantity. And this I show you here. The different colors indicate different energy densities, where energy density 0.5 indicates infinite temperature. So indeed, as you lower your energy density, the peak drifts to the right. And if you now extract the position of the peak and plot it as a function of energy density, you indeed see that it's very consistent with the prediction for the mobility edge for this model, up to some finite size corrections drift. But we check the finite size scaling that indeed this approaches the analytical prediction very well. So here we have now a nice framework how to also study the mobility edge in a given many-body system. And to now fully show that this is still consistent with maximal chaos, we look at the scaling of the maximal fidelity, and we find that at each energy density, the maximal fidelity scales with the density of state squared at this given energy density. So this is also consistent with maximal chaos. And this also motivated us to extend the finite ergodicity ansatz also to finite energy densities. In this case, we don't have really a full analytical picture how the time scales change while you approach the ground state. But what we can do, we can simply look at the off-diagonal matrix elements, and we can simply look how they scale as a function of energy density and interaction alpha. And this is what I show you as the density plot, where the density here is given by this exponent alpha. And indeed, along the mobility edge, we see that there's a divergence of the exponent eta, and it follows the mobility edge very well, which means that you have finite ergodicity not only as a function of your interaction alpha, but also as a function of your energy density while you approach the ground state. So the picture is now a little bit modified. I have a TH limit. You have here everything in between contours which are given by finite ergodicity and a fixed eta, until you hit the mobility edge where you have maximal chaos and the critical point to localization.
But there is not a line that fading ergodicity, right? Or
I mean, you can think of it as contours, because for a fixed eta, you can maybe draw kind of like a contour where the eta would be constant, like a constant eta contours. So finite ergodicity, yeah, it's everywhere in between ETH and ergodicity breaking, yeah. The contours they're complex to draw. I didn't draw them, but you can think of them like a kind of Gaussians in the energy. And that brings me to the conclusion of the first part of my talk, where I showed you first that finite ergodicity can be seen as a candidate scenario which maps a perfectly ergodic system to an anergodic system, and how the time scales change in your system, and how it actually happens that ETH is broken. This new phase is still ergodic, but the fluctuations do not comply with conventional ETH. And secondly, I showed you that finite ergodicity directly implies maximal chaos, so directly implies the divergence of the fidelity susceptibilities, and that finite ergodicity and maximal chaos follow the mobility edge precisely, which means that temperature-driven transitions also feature fading ergodicity. And I don't know how much time I have for the last part.
how long would you need?
7-8 minutes.
Okay, so that's-
Okay, great. And the last part, I want to switch gears a little bit and tell you about a scaling theory, which indicates different properties of a system, which obeys finite ergodicity. But first, what is scaling theory? As you already pointed out before, the Anderson model only has a transition in dimension 3 and above. This was a very open question in the 60s and 70s, where there was no easy solution why the two-dimensional Anderson model should or should not have a fixed transition. And given few simple arguments, the gang of four, or Abrahams, Anderson, Lichtadelo, and Markishnan, they presented arguments that in the metallic phase, you simply satisfy Ohm's law, and the conductivity has this particular dependent on your system size, linear dimension of system size. So it's the volume divided by L squared. While in the insulated phase, because we have localized wave functions, your conductivity should also be effectively localized with a similar localization length. Using these two simple ingredients, one can develop a beta function as a logarithmic derivative of this conductivity, which in the localized phase depends logarithmically on the conductivity, but in the purely delocalized phase should approach a plateau. And this plateau is only above 0 for dimension 3 and above. Why is that important? Because in the framework of a renormalization group, which the beta function where it enters, you have only a transition if the beta function is a 0, which is known as a Wilson-Fisher fixed point. And only if you have a 0 of the beta function, you can have actually a finite transition in your system. And for dimensions 1 and 2, you will never cross 0 because 1 never even approaches 0 any closely, and 2 goes to 0 asymptotically in the thermodynamic limit at when your disorder is infinitely small. So you always are close to 0, but you will never cross it, so you never have a transition. For finite system, you can see some form of transitions, but these transitions always go with disorder to 0, so you're always localized. And this story was revisited recently using modern observables. So what you can study is you pick your eigenstate in the computational basis, which here is simply your lattice. You take the coefficients of your wave function and you study the information entropy. And from that, you extract the fractal dimension. And this quantity, what it tells you is that if it's 1, your wave functions are delocalized in the entire lattice. So they spread the lattice more or less uniformly. If you're localized, then the fractal dimension goes to 0, and your wave function is approximately only has weight very close to some localization center. But if you can also have something which is in between, where you have a fractal dimension between 0 and 1, and then you have multiple localization centers, and your wave function become multifractal or fractal. And using this fractal dimension, sorry, using this fractal dimension, you can develop again a scaling theory where you simply consider the beta function of this fractal dimension, so the logarithmic derivative of d to the volume v. And considering this indicator, you can show that indeed you have the randomization group flow has a particular easy dependence where it goes here to an ETH fixed point where d is 1. You have a localized fixed point at d0. And then if your disorder is low, then you have finite size hairs which go toward the 1 parameter scaling and then towards the localized fixed point. But if your disorder is large, but if your disorder is small, then the finite size hairs go on the 1 parameter scaling, and then they ultimately go to the Gaussian fixed point for the ETH.
What are these lines?
Yes, these lines, they are the numerical values of this beta function. So if you have single parameter scaling, it essentially should collapse onto one curve, because you should only have dependent on one relevant parameter. But here they find some small finite size corrections. They call them hairs. But still at sufficiently strong large system sizes, they collapse onto a 1 parameter scaling.
So just D is, what is just D? There is D1 and there is D.
D is D1. They
Is
just
D1,
left the
okay.
subscript, yeah. So this is still D1. But you can develop a similar scaling theory for any D. Yeah, for any fractal dimension.
Okay, and then let me try to understand. So these lines is they get 1 point for each system size. Is it? And this
yeah, I mean they don't show it at point, but here this should be like each of these lines is one disorder strength and various system sizes. So this is a function of system sizes. These
okay,
are.
so each line is one disorder strength, and then you go along
Yes.
different size for. Okay.
They probably do some interpolation between system sizes to do derivative, because here you have to do a derivative with respect to the volume. So they do some interpolation and then the derivative.
And then there is the blue line, is someone.
The blue is kind of an expectation how your beta function would approach the ergodic fixed point,
Okay, fine.
which is also an interesting
I would
property.
have to go there along with that line until I go into
Yes,
the
exactly. Yes, exactly. And one important property which they can extract from the scaling theory is the critical exponent, which is given by the slope of the beta function. And what they find is that the critical exponent is roughly 1.5, with which more or less confirms what previous studies also have found. And they also can find what is the fractal dimension at the critical point, which was believed to be 2/3, and they see a very close to the 2/3 prediction. Yeah, 2024, yeah, it's new. So here they essentially showed the same kind of argument. You have single parameter scaling, and they also showed again that only in dimension 3 and above you have single parameter scaling and the critical point, so 0 of a beta function. And we wanted to see whether we can develop a similar kind of scaling theory, which here again I show you a sketch how it looks like, that you have finite size hairs going towards a 1 parameter scaling. Whether we can develop a similar scaling theory for interacting models, so here for the quantum sun model. And what we actually show is that for the quantum sun model, because we have fading ergodicity, what we will actually see, we will have a 2-parameter flow instead of 1-parameter scaling. So you have some 1-parameter scaling, which you can actually find. And then there are corrections on top of that, which are, although they will disappear in the thermodynamic limit, they are still relevant for finite systems. So you will never have actually 1-parameter scaling. And this 2-parameter flow, we consider for the single side entanglement entropy. So what we do, we simply consider the side which is most weakly coupled to the rest of the system and trace out the remaining part of the system. And we calculate the fundamental entanglement entropy of this single side. And then we normalize it by log 2, because for a ergodic system, this should go to log 2. And this quantity is very interesting because one can actually show that it directly relates to fluctuations of your diagonal matrix element of the magnetization at the same site. So because of that, we can simply use fading ergodicity, and we can show that we can argue that entanglement entropy has the same corrections as the fluctuations of the diagonal matrix elements. So it's given by some exponential decay with an exponent, I call it here eta prime, but it's proportional to eta. There's some prefactor which enters here.
And again, that prefactor does not depend on the different.
Yes, of course, yes. That's always important, yeah. And we now tested that ansatz, and for numerics for different values of G0, which was the prefactor and the interaction term, we see very nice agreement with this kind of functional ansatz to the numerical data for all the values of alpha in the ergodic regime up to the transition point. Now, in the localized side, we want to say, we will argue that given that we again have localized wave functions in the Hilbert space, the entanglement entropy should also feel some form of localization with some localization length. And here we simply say that the single side entanglement entropy decays exponentially with system size. And we also confirm this numerically up to very small alphas, that it indeed has this kind of exponential decay up to some finite number of realization fluctuations, because we couldn't go with large system sizes to large number of realizations. But it's pretty much consistent with what we're expecting. But we want to go a step further. Now, having these two ingredients, we want to make an ansatz which captures both phases in the model. And surprisingly, this can be mapped with this kind of Fermi Dirac distribution function, where now we have this eta exponent, which on the ergodic side becomes eta prime, but on the localized side becomes eta localized. And surprisingly, it actually happens that eta localized is minus eta of the ergodic side, that there is some symmetry, which we don't understand why exactly the same exponent should enter on the localized side, but it appears very consistent that there's a symmetrical divergence from both sides. So this scaling ansatz actually behaves quite well because we tested numerically again, and actually behaves much better because it also captures the small bends at very small system sizes. So it is a much better fit to our numerical data than the previous simple ansatz, both of the ergodic and for the localized side. We see that this ansatz works very well.
And then L0?
And the L0, yes, it's L0 we introduce as a model parameter dependent length scale, because as you can see here, we have some form of, let's say, crossings of these different curves. And this you can see as, for instance, L0. Alternatively, what you can say is that you absorb L0 to A, because here A we say is independent, but if you absorb L0 to A and put then L to 0, then you have some finite value at L0, which you can also see here. So there is some parameter dependence in the function which should enter, which can enter either through A or L0. But here we put it through L0 and we interpret it as some form of length scales, which will be important later on. But given that we have now a quite nice ansatz for the single-sided argument entropy, we can calculate analytically the beta function for this observable. And what we find is that the beta function looks like this. There's some logarithmic divergence, logarithmic approach to the critical point from above, and it decays logarithmically to 0 and to minus infinity on the localized side. But here one can already see, because L0 has some alpha dependence, that this beta function is not single parameter scaling. But at the transition, where L0 is relevant, L0 is basically 0, we can extract the critical exponent as the slope of the beta function at the critical point. And we see that the critical exponent is exactly 1. So with that, we want to argue that if you have an ergodicity, then the universality class corresponding to that should have a critical exponent nu equal to 1. Now there's also an open question what are the other critical exponent. We are still working on that. But at least this one critical exponent we can extract analytically and show that it's exactly 1. And now to actually motivate that we don't have single parameter scaling. Now we have this L0. If we now consider the beta function in terms of L prime, which is L minus L0, what we can actually argue is that this beta nu has 1 parameter scaling. But as a trivial consequence, since beta nu has 1 parameter scaling because we absorbed L0, which is the second relevant parameter, it means that the regular beta function has 2 parameter scaling. And numerically, it looks like this, that indeed, if you look at beta nu, it collapses into a single curve indicating single parameter scaling.
This is numerical result?
Yeah, the different colors are numerical results. It's the same. Yes. The different colors are different alphas, and it's again as a function of system size. And the arrows, which are not seen so well here, are how the system size increases. So these are like flows in your RG sense. And if you now go for beta, so the regular beta function, you clearly see there's a 2-parameter flow. And the dotted lines are the analytic expectations, which don't work precisely well when you're very close to the critical point, but they are almost exact if you're in the fading regime and close to the ETH regime. So these dotted lines show that indeed there's another relevant parameter in your model, in your theory, which breaks single parameter scaling. But using all these tools, we actually can show that this beta function is actually this single parameter scaling beta function, plus some corrections which decay as 1 over L. So asymptotically, you actually have single parameter scaling in the thermodynamic limit, but for finite systems, you always have large finite size effect, large finite size corrections, which are relevant for your scaling theory. And with that, I also want to conclude the second part of my talk, where first I showed you that if you have an ergodicity, this directly implies 2-parameter scaling. Secondly, what we can predict the critical exponent to be exactly 1 for the finite ergodicity. And as a kind of outlook, other possible scenarios of ergodicity breaking or like other possible scaling theories describing this kind of phenomenon. What are different kind of transitions having the same universality class with nu equals to 1, with the same kind of properties? Then some trivial consequences is that if L naught is 0, then you have always single parameter scaling, because L naught determines the second relevant parameter. And there's a natural question, how L naught depends on your model parameters, whether it's always finite, whether it's fixed, how it's whether it diverges at some point, because these questions are relevant. And with that, I want to thank you for your attention.